nanoparticles on confining light to improve the optical performance of solar cells. This is work I've done with my students at my research lab at the Independent University of Bangladesh. I know this is the title of the topic is it's quite heavy, so I'll try to make it go as simple as possible to many of you who are not versed with this research topic. So we know that what is the problem statement? The problem statement is commercially deployable solar cells have about 15% efficiency, which is actually quite low. What basically means that for every 100 photons of light that it absorbs, it's only creating 15 electrons, which is the units of electricity. So there is 85% of the light energy being wasted. Now, there are many fancy solar cells that have been developed in labs all over the place, but we're talking about commercially deployable ones. And as a result, solar cell technology has not been able to, unfortunately, replace the need for fossil fuels across the world. Now, so we see that there is a room for a lot of improvement for designing novel solar cells to give us more efficiency, because 85% of the energy is now lost. So there's room for developing solar cells at the nanoscale, where you can engineer solar cells to be more efficient than just 15%. Now, there are many groups around the world which are doing different kinds of design modifications. And in our research lab, we do basically simulation work. This is all simulation work. We simulate different kinds of solar cells where using plasmonic nanoparticles. These are specific nanoparticles made of specific metals such as aluminum, silver, gold. These nanoparticles can be placed on top of the solar cell, and they have this property called surface plasma resonance, which helps to absorb light more efficiently. So if you place them on top of the solar cell, they'll absorb light and then pass it on to the solar cell itself. So they aid the solar cell in absorbing more light. And that's what we work with in our simulations. So here, what we're doing here is we're defining this structure called a bow tie nanostructure, where we have two triangular pyramids. In fact, I think there's a laser pointer. Okay. So we have these triangular pyramids and the spherical particle in between. And remember, this is just a schematic, and this is what we're working on. And so this is a bow tie structure. Remember the name. Now, we use aluminum in our simulations because it's actually, from a fabrication standpoint, we thought ahead that it's cheaper and widely abundant, and it's also making these triangular nanoparticles is actually quite possible, and is what is shown in the literature by several techniques. One of them is interference lithography. But one of the issues are when you actually do the fabrication, we do the simulation with these kind of sharp edges, ideal particles. But when you actually simulate them, you actually get defective particles with round edges. It's very difficult to maintain a very sharp edge. So the question we wanted to do, or we wanted to investigate, is what happens in real life. I can simulate in a computer whatever I want, an idealized situation. But when you're actually fabricating it, due to the defects or limitations of the fabrication process, how much of my solar cell improvement is going to be affected either positively or negatively. And that's what we wanted to investigate. So we used the commercial numerical ANSYS numerical software package, where we used finite difference time domain simulations to do the optical simulation, and the charge solver to do the electrical simulation to get electrical parameters such as open circuit voltage, fill factor, efficiency, and the FDDT does calculate the short circuit current density, the optical generation rate. Now, some of the literature review tells us that there is definitely a decrease in the solar cell cost annually, but further decrease in prices will be problematic because of material supply limitations. Thin solar cells, which are basically thinner solar cells, therefore play a big role in potentially overcoming this problem. In the past, we have also shown these bow tie nanostructures of plasmonic nanoparticles actually can help us improve the solar cell efficiency. The previous studies focused on nanoparticle height and length. We're trying to figure out what are the dimensions. This work focuses on examining the edge sharpness of these particles. Fundamentally, what happens is the bow tie structures, the two triangular particles acts like an antenna or like a magnifying glass, which concentrates the light in between the particles. And then when you put a third particle, as you saw, the spherical particle, that helps to absorb the light more and send it over to the solar cells. So triangular particles are having, when you actually make them, you have these rounded edges, and that's what we're going to simulate. So our schematic for our simulations, we have the solar cell, the bow tie nanostructures made of aluminum placed on top of a silicon solar cell, and the light is coming from the top and it's going towards the bottom. What we basically wanted to do is instead of having the sharp edges only, we defined these triangular particles to have rounded edges, and we defined three parameters. C is the radius of curvature of each edge, or we can say a measure of the defect. And R is the center, the distance from the center of the triangular particles to the edge, and your Z span is the height. And what we are trying to simulate and figure out is what happens as I go from my idealized state to a more rounded particle in different increments. How does that affect my solar cell performance? First, we did a manual set of simulations doing a parameter sweep where we varied the sharpness, the height, the triangle radius, and the curvature. And we monitored, all the time we were monitoring by varying these physical parameters, what's happening to the current being produced by the solar cell. But we saw that we are making hundreds of simulations, and then we come up with a result. But then that's not a globalized result, because if we have 500 simulations more, we might have a result which is outside our current simulation base. So it's basically, the larger your sample size, the more globalized results you can get. But that'll take forever. So we have to come